Well, let's tackle this one using geometry. You're welcome to sketch it out yourself, either on an electronic drawing package or draw it out with a protractor and a ruler. Knock yourself out. But I want to do this with geometry because it's easier for me, and I think it's good for you to learn it this way. Planes flying 100 miles an hour at 16 degrees north of east. I'm going to try this by the Law of Cosines method here. This plane is going with a speed of 100 miles an hour at 16 degrees north of east. So the first thing I want to do is I'm going to establish what north and south and east and west are on my sketch here. So here's east and here's north. And this is going northeast 100 miles per hour, 16 degrees northeast. So I'm going to draw a vector to represent that. There's 100 miles an hour, and that angle there is 16 degrees north of east. The wind is 25 miles an hour at 5 degrees north of west. So, alright, so this is a 5-degree angle. Now what I want to do is I want to make a triangle that I can then use the law of cosines and law of sines to solve the problem. So I'll slide this over here and redraw as a triangle. So I'm going to start that over here. I'll start down here. Here's my 100, and then here's my 5. Now, if this angle was 16 down here, then the angle between the east-west parallel line there would also be 16, and then north of that east-west line, this is an additional 5 degrees. So this total angle here between these two vectors is 5 degrees plus 16 degrees, which is 21 degrees. So let's scooch down here and redraw this triangle. I've got a 100, and then I have an angle coming, a 25 coming up here, and the angle between these we decided is 21 degrees. So what we're interested in is finding the resultant, which is going to start here and go to there. And we'll call it R. The law of cosines tells us that that R is going to be equal to the square root of 100 squared plus 25 squared minus 2 times 100 times 25 times the cosine of the angle that's opposite R, which is that 21-degree angle that we figured out there. So 21 degrees goes in there. Alright, let's grab our calculator and do this calculation. Make my calculator big here. Let's see. 100 squared plus 25 squared minus 2 times 100 times 25 times the cosine of 21 degrees. And I need the square root of that, so I'll raise it to the 1/2 power. And here's my answer. The size of my resultant, the speed of my plane, ground speed, is 77.2 miles per hour. Now, the other thing that I needed to find is what is the bearing? What is this with respect to north and south and east and west? Well, I can find this angle using the law of sines. Let's call it alpha there. The law of sines, remember, says that the sine of alpha over 25, which is opposite from it, will be equal to the sine of 21 degrees, which is opposite R, divided by R, which we now know is 77.2 miles per hour. So going up to my calculator and multiplying the sine of 21, so it'll be sine 21 degrees times 25, and then dividing that by 77.2, I get a number that by cross multiplying and dividing is going to be equal to the sine of alpha. So the sine of alpha is equal to that number that's up here in the calculator. the 0.116 number. So alpha is inverse sine 116, no, 0.116. Well, let's find out what that is. I'll just go second function sine, oops, second function sine, so that's sine inverse, and then I'll just paste the answer in. Hit enter. Alright, so my angle here is 6.6 degrees. Alright, but that's not really my bearing. If I go back to the original drawing, what I've got here is I'm finding that this is 6.6 degrees from the 100 vector. So going back to here, my resultant, there's my R, is 6.6 degrees from that vector, which is already 16. So if I sum those up, well, that tells me that I'm 22.6 degrees and I'm north of east. So that's the bearing, or the heading, the direction of my resultant vector, and the size, the speed, well, that was my 77.2 miles an hour. In addition, I could also do this with other methods. I could graph it out. I could do the resolving vectors method, where I split it up into east, west, and north-south components and add them up. That's probably how I would typically do this problem, but I'm doing this just for a little perspective. Okay, we've answered this problem. Let's move on to the next one. Okay, let's start out solving this problem. A boat's heading straight across a river. It's going 1.5 meters per second. The current is 0.3 meters per second. Here's how we can model this with vectors. Let's imagine that here's our river. Here's one river bank, here's the other river bank. The boat is heading, he's trying to go, here's my boat, trying to go straight across the river. And the size of this velocity vector is 1.5 meters per second. That's how the boat is trying to go. The current, however, is changing things. So I've got a current here that's going down, let's say down is down the page. It's 0.3 meters per second. It's obviously not to scale. The 0.3 would be much smaller than the 1.5. Now, the question is, what's the actual or resultant velocity of the boat? Well, we can make a little triangle out of this. We already sort of have. This is 1.5. The current is 90 degrees, we're going to assume, from the boat, because it's trying to go straight across the river, so that's a 90-degree angle. And then we want to find what is the resultant velocity of the boat. Well, this is a Pythagorean theorem problem to get the speed. So it's just going to be, this resultant is going to be equal to the square root of 1.5 squared plus 0.3 squared. Let's pull our calculator up and we'll do this 1.5 squared plus 0.3 squared. Get our answer, take the square root, and so we know our resultant speed. It is 1.53, just a little bit faster actually than the boat can actually go, but it's not going straight across the river at the boat's speed. We also need to know, the other thing we got to find is we have to know what is its bearing, its angle. So we're interested in knowing this angle. I'm going to call it theta. And we can use tangent for that, remember? The inverse tangent of the opposite, which is 3, over the adjacent, which is 1.5, well, that's going to give me my angle. So alpha is, let's go back to the calculator, second function tangent gives me inverse tangent, 0.3, it's supposed to be 0.3, divided by 1.5, close my parens, hit enter. So it's 11.3 degrees downstream, I guess is how I could say it. Here's another step to this problem. It's asking here, if the river is 300 meters wide, how far downstream does the boat land from where it started? Here's my river, bank 1, opposite bank. My boat is moving across the river, and it's going at 1.5 meters per second. That's its speed. The boat is being pushed down the river at 0.3 meters per second. I know how far it is across the river because it tells me. It says that it's 300 meters wide. So that's how far the boat is going to have to go in this direction. At the same time, it's being pushed down the river. How far? Well, I don't really know how far it's going. However, I do know however far it's going, that is equal to its speed times time. So the distance downstream is equal to the downstream speed, or the current, times time. Well, I know the speed downstream, the current, is 0.3 meters per second, but I don't know what time is. However, the time that it drifts downstream is the same time that it goes across the river. And distance equals speed times time is also true for this motion. So distance across is the speed across times the same time. Well, I'll do a little algebra on this equation, and I find this. Time is equal to distance across divided by the velocity across, which is 300 meters divided by our 1.5 meters per second. When meters cancel out, my unit is going to be seconds, good time unit. And let's find out what the number is. Drag the calculator into the screen. 300, got to turn on. 300 divided by 1.5 tells me that I'm going to be traveling across the river for 200 seconds, which also means I'm going to be drifting down the river for 200 seconds. So the distance down is going to be 0.3 meters per second times 200 seconds. Now seconds are what cancels out, and the distance downstream will come out in meters. So if I take 0.3, multiply by 200, I come up with 60. So the thing has drifted 60 meters downstream in the time it takes for it to go across the river. Well, you have to practice a lot and do a lot of solutions graphically and with geometry to get really good at this. And I recommend you try all the methods so that you can pick out the one that works the best for you.